That sound, that's a sonic boom. It's loud, it's powerful, and it's the reason you haven't flown on a supersonic passenger jet in over 20 years. However, NASA has been quietly working on a revolutionary aircraft that won't boom, but thump. Just enough to hear it, but not enough to rattle your windows. Today, we'll explore the phenomenon of the sonic boom, the physics behind it, how iconic jets like the Bell X-1, the SR-71 Blackbird and Concorde made history, and how NASA's X-59 could shape the future. So strap in as we journey faster than the speed of sound. So let's start with the basics, and what exactly is a sonic boom?
Anytime any object goes faster than the speed of sound, it starts to generate shock waves around that object, whether it's an airplane, whether it's a bullet out of a gun, anything going faster than the speed of sound is going to create shock waves. When those shock waves travel to the ground, that's what our ears perceive as a sonic boom.
So, in simple terms, it's a shock wave in air, a powerful sound wave, created when an object moves faster than sound itself. To understand that, let's start with the speed of sound. Sound isn't instantaneous. It's basically pressure waves travelling through air. At sea level on a mild day, around 20 degrees C or 68 degrees F, sound moves at roughly 767 miles per hour, about 1,235 kilometers per hour. We call this Mach 1. An aircraft flying at Mach 1 is flying at the speed of sound. At Mach 2, it's going twice the speed of sound, and so on. Now, imagine an airplane flying through the sky. Even at subsonic speeds, slower than sound, the plane's movement pushes on the air in front of it, creating pressure waves. Basically sound waves that ripple outward. Normally, those pressure waves spread out ahead of the plane. But as the plane goes faster and faster, these waves bunch up. The plane is trying to shove air molecules aside faster than they can move out of the way. Eventually, when the plane reaches Mach 1, all those pressure waves merge into one strong shock wave that form at the nose of the plane. At that critical moment, we are breaking the sound barrier. The air can't get out of the way quickly enough, and a sudden change in pressure occurs. This is the birth of a sonic boom. However, a common misconception is that a sonic boom is a one-time bang, right when you break the sound barrier.
When an airplane does that, it doesn't just make shock waves one instantaneous time. It makes the shock waves as long as it's flying faster than the speed of sound. Therefore, a sonic boom that is created by an airplane travels with that airplane. So it's a common misconception that once an airplane breaks the speed of sound and breaks the sound barrier, you get a sonic boom and that's it. But that's not the case. As the airplane travels, it drags that sonic boom with it, and we call that the sonic boom carpet. Everywhere that sonic boom touches the ground as the airplane flies.
You can picture it like the wake of a boat spreading out behind in a V-shape. It's a 3D cone of pressurized air trailing behind, widening as it goes downward to the ground. Only observers inside that cone will hear the boom. If the cone doesn't touch you, you won't hear a thing. That's why someone on the ground hears a sudden boom after the plane has already flown past overhead. The plane is long gone, but the shockwave cone sweeps by you, and boom! It's like getting hit by a brief blast of sound energy. What does that blast actually sound like? Typically, a sonic boom is heard as a sharp double bang or a single loud boom. Why a double bang? Because usually two main shock waves form, one at the aircraft's nose and one at its tail. For a smaller aircraft or one flying very high, those two booms blur into one big boom that just sounds like an explosion or thunderclap. But for a larger vehicle like the Space Shuttle, people often distinctly heard two booms in quick succession, boom boom, as the nose shock and tail shock arrived separated by a fraction of a second. In either case, it's the sudden pressure change, essentially a pressure jump then drop, hitting your eardrums that make it such a jarring sound. Interestingly, the total change in air pressure in a sonic boom isn't huge, often on the order of only a few pounds per square foot above normal. That kind of pressure change is about what you'd feel riding an elevator down a few floors. The reason it sounds so loud is the rapidity of that change, a near instant bang rather than a gentle up-down in pressure. This shockwave trailing behind the aircraft forms an N-wave pattern, named because if you graph the air pressure, it looks like a stretched out letter N. The pressure rises sharply, then declines and goes slightly below normal, then suddenly jumps back to normal. This pattern is why there can be two distinct booms, one when the pressure first jumps up, and another when it jumps back up at the end of the N-wave. Now, how far does this sonic boom carpet reach? Everyone under this moving carpet will hear the boom as the plane passes. The width of the boom carpet depends mainly on the plane's altitude. As a rule of thumb, it spreads roughly 1 mile in width for each 1,000 feet of altitude. So, a jet flying supersonic at 50,000 feet could produce a boom carpet about 50 miles wide on the ground beneath it. Directly under the flight path, the boom is loudest, and it gets weaker towards the edges of that carpet. If you're right under a supersonic jet, you'll get the full boom effect, whereas someone a bit farther off to the side might hear a distant rumble or maybe nothing at all if they're outside the cone. Let's break down the physics just a bit more without getting too dry. Remember how the shockwave forms a cone behind the plane? The faster the plane, the skinnier, more pointed that cone is. At just over Mach 1, the cone is fairly wide. At Mach 2 or 3, it narrows significantly. The angle of this Mach cone is determined by the ratio of the speed of sound to the speed of the object. In fact, there's a simple relation. Sine equals v sound over v object. Don't worry about the formula. What it means is that if you go faster, the angle sine gets smaller. For example, at Mach 1.4, the cone angle might be around 45 degrees. At Mach 3, it could be around 20 degrees. This is why supersonic planes often outrun the sound they make. The sound waves are confined to that narrow cone chasing the plane, not radiating all around. Observers on the ground hear nothing at all until the moment the shock wave sweeps over them. 1 second it's quiet, next second, boom. The plane is already far ahead because the sound was literally left behind and just caught up to you. But how do we get to creating sonic booms? To understand that, we need to travel back to the late 1940s. Pilots and engineers were itching to find out if we could push an aircraft past Mach 1. Back then, some people even wondered if a plane might be torn apart by the turbulence and forces at the sound barrier. Early high-speed dives in World War II aircraft had seen controls freeze up or wings flutter near Mach 1, feeding the idea of a destructive barrier. It took a special aircraft and a brave pilot to finally go supersonic in controlled flight. Enter the Bell X-1. This was a rocket-powered bullet with wings, built specifically to break the sound barrier. On October 14, 1947, over the Mojave Desert in California, Captain Chuck Yeager flew the orange Bell X-1, nicknamed Glamorous Glennis, and became the first human to officially fly faster than sound. Yeager's X-1 was dropped from a B-29 mothership, ignited its rockets, and zoom! It reached about Mach 1.06, 700 miles per hour at 43,000 feet. People on the ground heard the first man-made sonic boom from an aircraft in level flight as Yeager cracked through the Mach 1 barrier. That achievement opened the floodgates. Once it was proven possible, engineers rapidly moved to design faster jets. By the 1950s, jet fighters like the F-100 Super Sabre were routinely breaking Mach 1 in level flight. The Bell X-1 showed that with the right design, a streamlined shape like a bullet, very thin wings and powerful engines, supersonic flight was achievable. In fact, the X-1's design and the British experiments with the Miles M52 revealed one key solution for control. It had an all-moving tailplane, stabilator, because a hinged elevator can lose effectiveness near Mach 1. This innovation of a moving tail would become standard on later supersonic aircraft. So, flying faster than sound isn't just about brute engine power, though that's certainly important. It turns out aerodynamics and materials had to evolve drastically to make supersonic flight practical. Let's talk about some of the key challenges engineers face when designing a supersonic aircraft. The aircraft's shape must handle the formation of shockwaves without losing control or creating too much drag. Early jets learned the hard way that thick wings and blunt noses won't cut it. supersonic planes use thin, swept wings or delta wings, and slender, pointed fuselages to slice through the air. A concept called the area rule was discovered in the 1950s. To minimize drag at transonic speeds, around Mach 1, the cross-sectional area of the plane should change smoothly, leading to that distinctive wasp waist or Coke bottle shape on some supersonic jets. The goal is to avoid sudden pressure buildups that make huge drag. Essentially, you design the plane so it disturbs the air as gently as possible, even when going supersonic. Going supersonic needs power. The Bell X-1 used a rocket engine because early jet engines weren't powerful enough. By the 1950s and 60s, we had afterburning turbojets that could push fighters past Mach 1. But an engine itself has a problem. Turbojet engines can't inhale supersonic air. The airflow must be slowed down before reaching the compressor blades. This is handled by clever inlet designs. For example, the Concorde and many fighters have variable geometry inlets, moving cones or ramps that create shock waves in just the right way to slow the air from, say, Mach 2 to subsonic speed by the time it hits the engine, all while avoiding instabilities. The SR-71 Blackbird had prominent shock cone spikes in its engine intakes that automatically moved to regulate the air and tame the supersonic blast of air entering the engines, allowing it to cruise at Mach 3+ without choking the engine. If you stick your hand out of the car window at high speed, it gets warm from air friction. Imagine that at 1,500 miles per hour. Air friction and compression at supersonic speeds generate tremendous heat on the aircraft's skin. The faster you go, the hotter. Concorde, which cruised at about Mach 2.0, would see its nose and leading edges heat up to around 127 degrees C, 261 degrees F. It actually grew by almost a foot in length during flight from the thermal expansion of its aluminium skin. The SR-71 flying at Mach 3 got even hotter. Parts of its titanium skin reached over 300 degrees C, 572 degrees F or more in flight. Aluminium would weaken and melt at those temperatures, which is why the Blackbird was built primarily from titanium and had to leak fuel on the ground. The metal panels didn't fit tightly until heated and expanded in flight. High-speed aircraft often require special alloys, thermal protection, and careful engineering to deal with this heat. Even the paint matters. Concorde was painted white to reflect heat. One time, Air France painted a Concorde in a blue Pepsi livery for a promotion, but they were advised to keep it at Mach 2 for no more than 20 minutes at a time because the darker paint could cause extra heating. Flying faster than sound means dealing with higher aerodynamic pressures and stresses, especially during maneuvers. The aircraft structure needs to be very strong but also lightweight. This often means using advanced materials, titanium, high-strength steel, composites in modern designs, and careful engineering. It also means you often fly high, 50,000 to 60,000 feet for Concorde, up to 80,000 feet for SR-71, to find thinner air and reduce drag and stress. Early on, little could be done about the loudness of the boom except flying higher, which helps since the wave weakens over distance. For example, an aircraft at 50,000 feet will produce a softer boom on the ground than at 30,000 feet because the shock wave spreads out more and loses intensity over the extra distance. Engineers also learned that a long, slender airplane produces a weaker boom than a short, stubby one. This is partly why supersonic aircraft tend to be needle-nosed and slim. By spreading out the change in pressure over a longer vehicle, the shock waves don't merge into as strong an N wave. In technical terms, a higher length-to-width ratio can reduce the peak overpressure of the boom. This concept is at the heart of modern low-boom supersonic designs. All these challenges mean designing a supersonic aircraft is a balancing act. You need a shape that's sleek for supersonic flow, but still safe and stable at lower speeds for takeoff and landing. You need powerful engines, but also ways to mitigate heat and drag. And of course, early designs were done with slide rules and wind tunnels, no fancy computers yet, which makes achievements like the X-1 and later the Concorde and SR-71 Blackbird all the more impressive. Concorde was the most famous supersonic airliner ever. In fact, the only successful commercial supersonic passenger plane to see service to date. Flying at around Mach 2.0, over 1,300 miles per hour at 60,000 feet, Concorde could whisk 100 passengers from London or Paris to New York in just about 3.5 hours, cutting transatlantic travel times in half. It was the crown jewel of engineering for Britain and France when it entered service in 1976. Passengers on board dined on champagne while cruising at twice the speed of sound, often chasing the sunset across the sky. However, Concorde also left a trail of sonic booms wherever it went supersonic. This proved to be a huge issue for its operation. In the early days, people realized quickly that sonic boom noise would make supersonic flight over land extremely unpopular. The US, India, and other countries banned Concorde from flying supersonic over their territory due to the noise. This meant Concorde was mostly limited to routes over the ocean, where its booms would dissipate harmlessly over the water. Even on those routes, Concorde's pilots had to wait until they were out over the ocean before pushing through Mach 1, to avoid booming the populace on takeoff.
3, 2, 1, now.
Concorde had other challenges: deafening engine noise on takeoff, high fuel consumption, and eventually an aging airframe and a tragic crash in 2000. All those factors combined, economic, environmental, and social, led to Concorde's retirement in 2003. Many aviation enthusiasts look back fondly at Concorde's streak across the sky, and some people even remember hearing its distant boom as it traversed the ocean routes. In the realm of military jets, the Lockheed SR-71 Blackbird deserves special mention. This was a reconnaissance spy plane developed in the 1960s that could fly faster than Mach 3, over 2,000 miles per hour at altitudes around 85,000 feet. The SR-71's job was to outrun threats. If an enemy launched a surface-to-air missile, the Blackbird pilot would punch the throttles and literally leave the missile behind. In doing so, the SR-71 undoubtedly produced sonic booms along its flight path. But because it flew so high, those booms were spread out and weaker by the time they reached the ground, if they reached at all. In fact, typical booms from an SR-71 at Mach 3 and 80,000 plus feet were measured at around 0.9 psf, which is on the low end, less than half the strength of Concorde's boom. There were fewer complaints about the Blackbird's booms, likely because it usually flew secret routes, often over the ocean or hostile territory where civilians weren't filing noise reports. And it was far less frequent than, say, daily airliner service. From an engineering standpoint, the SR-71 was remarkable. Built largely of titanium to withstand heat, coated in a special black paint that radiated away heat, hence the name Blackbird, and designed with sleek chines and blended body for aerodynamics. Its engines featured those movable inlet spikes to handle supersonic airflow. It holds speed records to this day, like flying from Los Angeles to Washington, D.C. in just 64 minutes. And yes, it left a continuous boom trail in its wake across the sky. In its final years, the SR-71 was also used by NASA for high-speed research, including studies on sonic boom propagation at high altitudes. This helped scientists understand how the boom intensity varies with heightened atmospheric conditions. The Blackbird's legacy, beyond intelligence gathering, includes proving that routine flight in Mach 3 was possible and relatively sustainable if you nailed the technology. In the 1950s and 60s, as more supersonic jets, mostly military, took to the skies, people started experiencing unexpected booms. Imagine you're at home and a sudden boom rattles your dishes. You might think that something exploded nearby. As these occurrences multiplied, public complaints poured in. There were even deliberate tests. In the early 1960s, the US government conducted experiments over cities. For instance, Operation Bongo 2 in 1964 over Oklahoma City, where for months, jets deliberately created booms to gauge public reaction. The public's response? Overwhelmingly negative. Thousands of complaints and reports of minor damage, like cracked plaster and shaken nerves, made it clear that routine sonic booms over populated areas were not going to be welcome. A turning point came in the late 1960s. In one famous 1968 episode, a supersonic Air Force F-105 Thunder Chief jet flew low over West Oklahoma City and accidentally broke the sound barrier at only 50 feet altitude during the ceremony, producing an enormous boom that shattered around 200 windows and even injured some people with flying glass. This and similar incidents spurred lawmakers. By 1973, the US Federal Aviation Administration, FAA, banned civilian supersonic flights over land. These regulations had huge consequences. For one, they basically killed the market for supersonic airliners beyond Concorde. The US had its own SST project in the 1960s. Boeing was working on the 2707, but it was cancelled by 1971, in part due to environmental concerns and the realization that it couldn't operate freely over land. Concorde itself had to live with a constrained route structure. One major reason that it never became a widely used plane was that it simply couldn't fly supersonic to most destinations, and subsonic and Concorde is just an inefficient normal plane. Since Concorde, we've had a long lull in civilian supersonic flight. But that doesn't mean progress stopped. Military fighters like the F-14, F-15, F-22 and others have routinely hit supersonic speeds. The F-22 Raptor even supercruises at Mach 1.5 without afterburner. And they create sonic booms, which is why training routes for fighters are often over the ocean or sparsely populated areas. Yet, the big dream of flying passengers faster than sound has stayed alive. In recent years, several projects have emerged aiming to bring back supersonic travel without the sonic boom headache. The most prominent is NASA's X-59 Quest, Quiet Supersonic Technology Program. The X-59 is a sleek single-pilot experiment jet being built by Lockheed Martin for NASA. Its goal? Fly supersonic over land, but produce a sonic thump instead of a boom.
What we've learned since Concorde is there is a level of acceptable noise that people would be comfortable with hearing. So we've done a number of different studies on that. We've also gotten the tools to do the analysis of the shock waves coming through the atmosphere to the ground and seeing how they merge and change while they're going through the atmosphere. And then we've also gotten the tools to be able to design a quiet supersonic aircraft. A lot of it is leveraging all of the efforts that have been done. We've done a test years ago with an F-5 where we modified the front end of that aircraft. It was to show that you could change the shock waves and modify them and make a change to the signature on the ground. And so we're leveraging all of those years of efforts to, kind of culminating in this X-59 design.
The big breakthrough? Shaping the aircraft itself to control the shock waves.
The big things that make X-59 quieter is you can see the nose. That's pretty much a standout, right? The vehicle is about 100 feet long. The nose is only 38 feet of that length. And so that is one of the key characteristics. With shock waves, we're controlling where the shock waves come off the vehicle and the strength of the shock waves. And so with the nose, very gradual increase helps the shock waves be less strong and also kind of distributed. And then the other thing that's unique compared to Concorde is the engine being above the wing. We really tried to move as much as we could from the bottom. If you can see, there's really not a lot of disturbances, things that cause disturbances on the bottom of the aircraft that would cause shock waves. And one of the key ones would have been the engine. And so the engine being essentially shielded by the wing, the shock waves from the engine go up, but don't go down. And then the other thing we have is this little T-tail that's on the back. It's not used for control or anything like that. The position of it is used to kind of tailor and interfere with the other shock waves that are coming off from the surfaces and the engine exhaust. And so those are kind of some of the key things that contribute to it being quieter.
With the right design, you can spread out the pressure waves so they don't merge into one big boom. Instead, you get what they call a low boom, something more like a soft thump. It's about controlling how the shock waves come together, turning a wall of sound into a whisper. The X-59 is only at the beginning of its testing program. Traditionally, X-planes have been a bit like a Frankenstein monster with bits cobbled together from other aircraft. And the X-59 is no different.
With X-planes, we traditionally build the aircraft using many different components from other aircraft. Our engine is an F-18 engine. The canopy and the cockpit is a T-38 backseat cockpit. And getting them all to work together has been one of the challenges that we have had. And it's been really interesting to see kind of come together, especially during now these integrated tests where the aircraft is fully alive and working together. And
once the X-59 is in the air, the second phase of research comes into play. The X-59 is set to fly over select US cities, not to test its speed, but to test how people perceive the sound.
Concorde's sound was kind of at that higher level of like 100, 110 PLDB, but we're targeting somewhere 75 to 80 PLDB. So that's the difference between that loud thunder type versus the rumble in the distance that could, ultimately kind of incorporate into your everyday life. You wouldn't even notice that it was happening.
There is no suggestion that the X-59 won't work, but the next hurdle will be to persuade regulators to adopt a noise standard to allow overland supersonic travel.
The X-59, the part that I'm managing, is just one piece of the overall Quest mission. And the Quest mission's goal is to provide both international and domestic standards organizations the data from the community tests to hopefully change the speed limit, which is currently in place that says no supersonic commercial travel over land, to a sound limit. And so the mission will be successful when we provide the regulators the data on what is an acceptable noise level.
Imagine flying from New York to LA in under 3 hours without disturbing anyone on the ground. It could open the door for new commercial supersonic jets that are fast, efficient, and finally quiet. The quiet boom might be the key to unlocking the next era of air travel. There are already a number of companies working on creating the next generation of supersonic passenger airplanes. Boom Supersonic is in the early testing stages of a prototype as a precursor to a supersonic airliner equivalent to Concorde. Overture is more evolutionary than revolutionary.
We know how to create sonic booms of a whole spectrum of intensities, but the more we dampen it, the more we give up other things. We give up fuel efficiency, we give up range, we give up affordability of tickets, we give up sustainability. And so to be able to fly supersonic over land, we want to make it quiet enough that it's not a problem for the people on the ground, but not so quiet that it's a problem for the people in the air who then can't afford to fly on it. So there's this sort of balancing of the boom intensity with the economics of the airplane. And where we are today, there is no regulatory framework that says how quiet is quiet enough. And the effort to answer that question appears to be quite a ways off. And so it's not possible to design a quiet boom airplane today because we don't know how quiet it needs to be. So what we're doing is starting with where there are no impediments. And that's one of the really exciting things about Overture. Everything we need technologically to make Overture a success is sitting behind me on XB1. And everything we need from a regulatory perspective is already on the books. We don't need any new regulations. We don't need to invent anything new. It's just engineering. It's challenging engineering. It's difficult engineering, but it's just engineering. It's not science and it's not politics. And so that's our approach for Overture 1.
However, the company understands overland supersonic flight is crucial, And the work of the X-59 would make that possible.
Imagine a world where you could buy a ticket on United and fly from Tokyo to Seattle in 4.5 hours, but then flying from Seattle onward to Washington, D.C. is actually longer, despite that it's a much shorter distance. In that world, I think we're going to be able to show the world what a technically feasible kind of muted sonic boom is like. And then I think those regulations are going to change very quickly. And then that's going to enable supersonic business jets. It's going to enable supersonic airliners that can fly coast to coast, and it just gets much better. And so that's our approach. It's very hard to change the regulation without a lot of public excitement. And we're going to go generate that public excitement with Overture. And then that will enable us to go accomplish the political change that will bring supersonic flight everywhere.
Another company developing the next generation of supersonic aircraft is Spike Aerospace. It has a business jet on the drawing board, which will have similar characteristics to the X-59.
The secret is complicated, a lot of aerodynamics, a lot of physics in it, but what you're doing is you're designing the aircraft so the airstream that's coming and hitting the plane is dissipated. The shock wave that creates is dissipated before it reaches the ground. And you do that by adjusting the planform or the shape of the wing. We have a highly swept delta wing, similar to what the Concorde had, but we've changed a few other things to reduce that sonic boom. So it's really understanding how the sonic boom is formed and then minimizing the surfaces that interact with that airstream.
The X-59 may be a small experimental aircraft, but it's likely to be the genus for supersonic commercial aircraft of the future.
We look at X-59 as demonstrating the technology required to make a quiet sonic boom. So we expect future airplanes, commercial airplanes that carry people like me and you, to have the same DNA of X-59. So you're going to see long stretched out noses to make sure that the shape of the airplane changes gradually. You're likely going to see engine placement similar to X-59, somewhere where the shock waves from the engines can be shielded from traveling to the ground. So the DNA of the X-59 is going to be applied to future airplanes.
The next chapter in this story is being written now. Engineers and researchers are working on designs that muffle the boom, from the shape of an aircraft's nose to the placement of its engines, all aiming to make supersonic flight viable and neighbor-friendly. If they succeed, we might see a revival of supersonic air travel in our lifetimes. This time, not just as a Concorde-style luxury for the few, but perhaps more widespread. Imagine flying from Los Angeles to Tokyo in half the time, or doing a cross-country trip in 2 hours without causing a sonic ruckus below. The X-59's results, due in the next couple of years, will be pivotal. If that soft thump replaces the boom, regulators could open the skies again to faster-than-sound travel.
Remember to hit the subscribe button and ring that bell to stay updated with our latest content. And while you're here, why not check out another one of our exciting videos? Thanks for watching, and see you in the next one.